All right, so today we're going to be finding area of shapes using trig. When I look at these first two figures, and it says to use trig to find the altitude of each polygon below. When I look at the first polygon, it's a triangle, okay? If I were to draw on the altitude, we know the altitude is from a vertex perpendicular to the opposite side. So that's what I'm trying to find, is that altitude. That's my x. Okay? To use trig, we know we're supposed to be using trig. In order to use trig, I have to have a right triangle. When you draw on an altitude, you make right triangles, right? If I look at the left-hand side there, or both sides, it's really, I have a right triangle on the left side and a right triangle on the right side. They don't appear to be congruent. I'd need more information to know whether they are or aren't. But really, if I just want to find x, I'm just going to look at the left-hand side, because then I have a little right triangle where I know one of the acute angles, and I know it's hypotenuse, and I'm looking for a missing side. So I can use trig on this problem. If I put my smiley face right here, I can see that across from the right angle is my hypotenuse. And then, so the adjacent is down here, the unlabeled side. Just from here to here, it's not this whole piece down here. And then the x that I'm trying to find is the opposite side, which I almost labeled A for altitude because we were finding the altitude, but then I knew we were going to be working with adjacent and opposite, so I didn't want to have A's in the wrong place. So I just called it x for my altitude, the side I was trying to find. Okay? When I look at SOHCAHTOA, I can see on this one that I know my hypotenuse is 12, and I know I'm looking for the opposite side, so I can see I'm going to be using sine. Sine of the angle is 67, so I know I'm not using inverse, equals the ratio opposite over hypotenuse. My opposite is x, my hypotenuse is 12. Put the left side over 1 and cross multiply. X times 1 is x equals 12 times the sine of 67. That I'm ready to put in the calculator. Make sure that the last people who used your calculator didn't put it back in radians and mess you all up. Make sure right up here it says degrees. Someone in my last class who came up to me and said, my calculator, there's something wrong with it. It gave me wrong answers, the whole notes. And her calculator was still in radians. So make sure you're in degrees. We actually found with these calculators, you can use the little trackpad right here, and you can put your mouse over it, and it'll actually toggle between radians and degrees. So it's real easier than we even thought to switch it. Okay? So make sure it has a little DEG up there, and that's where you are. Okay? All right, so I'm going to do 12 times the sine of 67, and that's 11.046. 11.046, and my units here are going to be centimeters because that's what they are on my hypotenuse. Okay. The next one, if I want to find the altitude on this one, if I just go from the top straight down to a bottom, if I go from this corner and straight down, and make my 90-degree angle, then I don't have any information about that little right triangle, and I didn't make a right triangle on this side. I have like a weird looking trapezoid on that side. Okay. If I start at this one and come straight down to my altitude, remember you extend one side to see where your altitude ends. So there, that kind of is a little more helpful because I can see that I have one side is 20. I do need an acute angle, so I need to know that 58. If I'm not sure, though, that I have parallel sides, another thing we could do is we could move this to inside so that I can work with this right triangle. Because, right, that's still an altitude. It's just an upside-down altitude. It's still the vertex to the opposite side, so it's still an altitude. And then I can work with that triangle. And all three of those altitudes that I drew in will all be the exact same length. If this is a parallelogram anyway, they'll all be the same length. Okay? All right, so now I have a right triangle. I'm going to put my smile face at the 58-degree angle. Where's my hypotenuse? The 20. Where is my adjacent? The top. And then my opposite is the one left, and that's the altitude. That's the one I'm finding. I'm going to use an X for altitude instead of an A, so I don't get it confused with adjacent. And then I'm going to look at my trig function, so SOHCAHTOA. And I can see that just like last time, I know the hypotenuse. I'm trying to find the opposite, so I'm going to use sine, cosine, or tangent? Sine again. The sine of 58 degrees is equal to the ratio opposite over hypotenuse. Opposite is x, hypotenuse is 20. Cross multiply. X times 1 is x, and 20 times the sine of 58, I can figure that out. X equals 20 times the sine of 58, not 50. It's 16.961. And these are millimeters this time. All right, today we do want to focus on some area though, so I am going to be finding the area of some polygons. So I'm going to first start with the area of a triangle. Do we remember the formula for area of a triangle? Kind of. I heard it different ways. Yeah, let's go with base times height, and then it's half of that, right? So you can either, you'll see it in two different ways on a formula chart. You'll see it as 1/2 the base of the triangle times the height of the triangle. Or you'll see it as the area equals the base times the height divided by 2. But those are both the same thing, right? If you multiply base times height, dividing it by 2, or multiplying it by half, those are both doing the same exact thing. Okay? All right. So let's find the area of the given triangle. When I look at this triangle, I can see that the area is going to equal 1/2 the base times the height. I should have put that in parentheses also. So my area equals 1/2. What's the base of this triangle? 48. What's the height? We don't know yet. We have to find it. Okay, so let's come over here and let's find it, right? If I draw on the height, that's an altitude. So we're going to use trig to find it. I'm going to use the right triangle on the side that I know the acute angle on. That's the only angle in this figure that I know. So I'm going to use that triangle. I'm going to put my smiley face at the 23. Where's my hypotenuse? 32. Where is my adjacent? The bottom. Thank you for not saying 48, right? The 48 is not the adjacent. The 48 is all the way across that bottom, right? So the adjacent is this side that's also unknown. We can use trig to find it. We don't need to. But we don't know how long the adjacent side is. It's not 48. 48 is including this little bit over here. So it's not part of the yellow triangle. Which means the altitude or the height of this triangle that I need to find, which I'm going to put x, you could put h, but then you might get confused with your hypotenuse, is my opposite. When I look at SOHCAHTOA, Which two sides am I working with? Opposite and hypotenuse. So that's going to be which trig function? Sine. So the sine of 23 equals the ratio O over H. So O over H is going to be X over 32. Make a proportion and cross multiply. X times 1 equals 32 times the sine of 23. So let's see what that is. 32 times the sine of 23 is 12.503. So then my area, I just put this in the calculator. My area equals 1/2 times 48 times 12.503 gives me an area of 300.072. Do we know our units? Almost. Yes, because if I'm multiplying 48 feet by 12.503 feet, when I do feet times feet, I end up with feet squared. And you'll always get that with area. You'll always have two single dimensions multiplied together. So that's why your units always end up squared. So we have feet squared. Now, to the average person that's not sitting in a math class, if you say feet squared, that sounds weird. Like you don't go, oh, what's the square footage of your house? And somebody wouldn't say, oh, it's 1,000 feet squared. That sounds weird, right? We always usually talk about the square footage, so we say, oh, it's 1,000 square feet. And that just means 1,000 little square tiles that are 1 foot by 1 foot would fit in that area. In this triangle, the whole triangle, not just the yellow piece, but the whole triangle there that we started with, 300 of these little 12 by 12 tiles would fit in that triangle. The triangle's a little bit bigger than it looks there. Okay? But that's always why you see your units squared when you do area. Because you're always going to have two lengths multiplied together. Alright, let's remind ourselves little things we know about a regular polygon. We looked at the regular polygon yesterday, and we said it's a polygon where all the sides are congruent. So all of these sides equal each other. It's equilateral. They're all equilateral. All the sides are the same. So all of these. Now, that's not enough to make something, generally, that's not enough to make something regular. It's just the sides. Because we know we could take this right here and we can make it look more like a diamond. We could squish it so that it's a rhombus. And then all the sides would still be equal, but it wouldn't be regular. Because in order to be regular, the angles also have to be congruent as well. Which we know in a triangle means they're all 60. And in a square, we know that we're in a quadrilateral. We know that means they're all 90, which makes it a square. That and the equal sides. And we will learn when we get to unit 7 how big these are in a regular pentagon. And we will learn how big they are when we get to unit 7 in a regular hexagon. Okay? The center of a polygon is the point that would be the center of a circle drawn, the center of a circle drawn around there's a typo here, should say polygon. So if I were to sketch a circle around this triangle, the center would be the center of the circle that goes around. It would be the circumcenter on the triangle. Because remember there's like 4 different triangle centers. On your square, same thing. It would be the center of the circle that goes around the square. And same thing here on your pentagon. And same thing on your hexagon. It would be the same thing for a heptagon, an octagon, a nonagon, a decagon, an 11gon, a dodecagon. That's all you have to memorize. You don't have to memorize any further than dodecagon. And we don't even memorize 11. We just call it an 11gon. Great. All right. So those are our, oops, I didn't draw my last center in there. Those are our centers. Then the apothem of a polygon we talked about yesterday. It's the distance from the center perpendicular to a side, and it divides the side equally in half. So if I draw them all in, they're going to hit at a little 90-degree angle, and we know it's going to divide the side in half. That's my apothem. And then my radius is the distance from the center point to a vertex. And it's basically the radius of the circle that we drew around the figure. That's my radius. That's my radius. That's my radius. That's my radius. Notice when you put a radius and an apothem going to the same consecutive spots, we end up with a little right triangle, which is going to help us with trig. All right, so when I look at my example down here, it says point A is the what? Center. Segment RA is a radius. And AP, apothem. All right, so let's practice working with regular polygons. All right, find the apothem of the regular polygon below. So we did this yesterday. So these two aren't going to be new, these first two problems, and then we're going to switch to area. So yesterday, when we wanted to find the apothem right here, we said we need to work with this little right triangle. So if I were to re-sketch that little right triangle so that I can actually write inside of it, if the whole side along the bottom is 10, if each of my sides are 10, what is just one of these little, one side of it? 5. So I know that's 5. In order to find the apothem, we said, oh, let's find this angle up here. And we did that by dividing 360 by how many of these triangles we could fit in there. How many of those triangles, if we have 8 sides, how many of those triangles can we fit in? 16. So I have 16 triangles. So I'm going to find that central angle, the angle in the center, right? The angle by the center, so the central angle. I'm going to take 360 and divide by 16 to give me that central angle. And we did it yesterday. It's still 22.5. Every octagon you ever meet will all have central angles. Well, every regular octagon you ever meet will all have central angles of 22.5. So then when I put my smiley face and label my hypotenuse, my adjacent, and my opposite, and compare that to SOHCAHTOA, which two sides am I working with? Opposite and adjacent. So which trig function am I going to use? Tangent. The tangent of 22.5 degrees, it's not inverse because we know the angle, is the ratio opposite over adjacent. So I'm going to cross multiply. Am I going to multiply or divide when I'm done? Divide, because A is in the denominator. You can skip straight to that, but in my notes I like to write it out so that I remember why I'm dividing. I can see it's because I've got a times the tangent of 22.5, so I have to divide it out. So my apothem is 5 divided by the tangent of 22.5. Which is 12.071. What are my units? Inches. So there's my apothem. The next one, find the apothem of a regular pentagon with a side length of 12 feet. So for a pentagon, it's kind of like drawing a house. Bless you. Except your sides of your walls need to come in just a scotch. That's a math word, scotch. Not really, I made it up. Alright, we have a side length of 12, and we're trying to find the apothem. Okay, so I know I'm going to need to use this triangle. So when I look at that triangle, and if I make it bigger, how long is this piece along the bottom going to be? 6, because my side is 12. So half of it is 6. And then I need to figure out what this angle in here is going to be. How many triangles am I going to have if I have 5 sides? How many? Did you say 7? Oh, I thought y'all said 7. I was like, where did you get 7? Okay. 10, because there's 2 on each side, and there's 5 sides. Triangles. So we're going to divide by 10, which is 360 divided by 10? 36. So just like yesterday, we did a pentagon yesterday also. So it hasn't changed, and we're trying to find the apothem. Alright, so I'm going to put my smiley face at 36. Where does my hypotenuse go? The unlabeled side, the radius. Where does the adjacent go? By the A, the apothem. Meaning the 6 is on the opposite side we have to yell at. So katoa. I am working with the opposite and the adjacent. So again, it's going to be the tangent. Be careful. Sometimes they ask you to find the radius, or instead of giving you a side, they give you the radius. They're not always, won't always be tangent. It just happens to be a lot of the time tangent. Tangent of the angle 36. Since I know the angle, it's not inverse. Opposite over adjacent, 6 over A. So again, I'm going to end up dividing because the A is in the denominator. A times the tangent of 36 equals 6 times 1. Divide both sides by the tangent of 36. You can skip this step. Again, I like to put it in the notes. So my apothem, 6 divided by the tangent of 36, 8.258. What are my units? Feet. Nope, just regular old feet, because this is a length. It doesn't become squared until we do area, which, speaking of area, the area of a regular polygon is found using this formula. Notice it has 2 A's in it. Do you think it's important that one's capitalized and one's not? Yes. Capital A is always used to represent area. Guess what the little a represents? The apothem. Guess what the capital P represents? Perimeter. Okay. If you want to know where this formula comes from, it actually has to deal with if you were to break this into its 5 congruent triangles that come together to make up that pentagon. or up here, the 8 congruent triangles that you make by drawing in the radii. That's where the formula comes from, is based on finding the areas of all the little triangles and then adding them together. The formula reduces down generically to 1/2 AP. There's a video if you look at last year's resources, if you want to see the actual worked out process of finding that area formula. Okay? Alright, so in this problem, my example problem here, we're going to say area equals 1/2 the little a times the capital P. What's my apothem? 7.5. What's my perimeter? 10.9 times 5, which is? Good, 54.5. So this I'm going to put in my calculator. 1/2 times 7.5 times 54.5, and I get an area that is 204.375. These were both meters, so my apothem was meters. My perimeter was meters, so meters times meters, I'm going to get square meters. Area always has square units. The square cannot go on the number. If you put the square and you don't put the meters, if you just do 204.375 squared, that's a really giant number, because we're not actually squaring the 204, we're describing the 204. When we do the square meters, that's a description of this number. We're not squaring that number. Does that make sense? Okay. All right. Find the area of a regular octagon with a side length of 4. So an octagon, I never took art, so don't judge my octagon. What I do to draw an octagon is I draw an exploded square. I mean, like if you had a square and you put a little piece of dynamite in it and you set it off, the sides would all explode out like that, right? And then you just connect the corners. Don't judge me. That's how I do it. It doesn't turn out perfectly regular, but I mean, it's a little tall, but that's okay. It's an octagon. All right, I have a side length of 4. I know to do my formula, I'm going to be doing area equals 1/2 little a capital P. The capital P is pretty simple to figure out, because my capital P, if it's an octagon, I have how many sides? 8. And each side is 4 units long. So my capital P is easy to find. It is 32. So I'm going to replace the P with 32. But I need to figure out what I'm replacing the A with. That's the harder part. Okay? So to figure out what I'm going to replace the A with, I need to draw in my little triangle here. So I can find this little A. How long is the piece on the bottom of that right triangle? 2. Do we know what the angle inside is? It's still 22.5, right? It's an octagon. We've done an octagon. I think this is the 3rd time now. You don't have to memorize it, right? It's 360 divided by 16 is my 22.5. And that is that angle. So then if I put my smiley face here, which one's my hypotenuse? The unlabeled, the radius. And so which one's the adjacent? A, the apothem. Which means the 2 is the opposite. And when I look at SOHCAHTOA, I'm going to be working with the adjacent is what I'm trying to find. And the opposite is what I know. So again, I'm going to be using tangent. Don't always just go to tangent. It's not always tangent. Okay? All right. Tangent of 22.5. Oops. Is equal to, since I know the angle, I'm not doing inverse. Opposite over adjacent, opposite is 2, adjacent is A for apothem, not for adjacent. Over 1, when I cross multiply, I get A times the tangent of 22.5 equals 2 times 1. Since A was in the denominator, I know we're going to divide because we need to unmultiply the 22.5 tangent. So our apothem is 2 divided by the tangent of 22.5, 4.828. So that's what's going to go over here, 4.828 for my apothem. My area formula says it's 1/2 the apothem times the perimeter. So when I put that in my calculator, 1 divided by 2 times the apothem, 4.828, times the perimeter, 32, I get 77.248. 77.248. They didn't give me any units in this problem, so if I want to show the units, I could just say units, and I know it's 4.828 units times 32 units, so units times units is units squared. Again, that's just a description of the type of units. It doesn't affect the actual number. Questions on that one? All right. Find the area of a regular hexagon with a radius of 7. So for a regular hexagon, here's how I draw a hexagon. It's real fancy. I do a horizontal bar, and then I do a less than symbol, and then I do a greater than symbol, and then I connect the bottom. Hexagon. We have a radius of 7. In order to find the area, I know I'm going to need the apothem and the perimeter. And so in order to find the perimeter, I'm going to have to find one of these this little side, so that I can double that to find the whole side, so that I can multiply that by 6 to find the whole perimeter. Okay? First thing we need to do before we can even attempt trig is we need to know what angle we're working with, right? So I need to know this little angle right here. If I have a hexagon, how many triangles are going to be there in the center? 12. So 12 triangles, which means 360 divided by 12, which is 30. So if I were to redraw this triangle bigger, because that's too small for me to get in, I know this angle up here is 30, and this is 7. Oh, hold up. What kind of triangle is this? 30, 60, 90. It's a 30, 60, 90 triangle. If we remember our rules, and I know this is a hypotenuse, I can use my rules to just know the short leg. I don't have to use trig. I can do opposite and hypotenuse, so I can do the sine of 30 equals x over 7, calculate it. And then I can do the cosine of 30 equals adjacent over hypotenuse and find the adjacent, and then have my two numbers that I need. But if I don't even want to pick up a calculator, I don't have to pick up a calculator, because I know that if I have a 30, 60, 90, the 30 is my short leg, which is half the hypotenuse, so this is 3.5. I don't have to do any trig at all. I could, again, remember that would be the opposite over hypotenuse, so that would be sine. And we'd have x over 7, so we'd end up multiplying. So we'd have 7 times the sine of 30. So you could do trig. There's no need to. And then my long leg is my short leg square roots of 3. Which if I do trig, I would do cosine of 30 equals adjacent over hypotenuse, so a over 7, so 7 times cosine of 30. Which gives me a decimal, but guess what that decimal is equal to? 3.5 square roots of 3. Yay! Isn't that lovely? So your trig will absolutely work. If you don't remember your special right triangles, that's perfectly fine. If when we take the test, you come to some special right triangle problems and you're like, crap, I don't remember how to do special rights, do trig. Go get the right answer. Do trig. But if you don't have to do trig because you know the special right answers, you can be done really quick without having to write anything down. I didn't have to do any math. I just said, oh, 7 divided by 2. And then stick a square root of 3 on it, right? So I need my perimeter still. How long is a whole side? Guess what? Every hexagon you'll ever see, you'll end up with a 30, 60, 90, right? Because you're always going to divide by 12. So your radius and your side length in a hexagon, won't happen anywhere else, but in a hexagon, your radius and your side length will always be equal. Your radius and your side length will always be equal. So if one side is 7, there's how many sides? 6. So my perimeter is 42. So my area equals 1/2 A, 3.5 square roots of 3. If we did trig, we'd get more rounding error than without trig because you would have a decimal here that was rounded. My perimeter is 42. When we put that in the calculator, there we go. I'm going to do 1 divided by 2, parentheses, that's blurry. That's better. 3.5 square root of 3. And then notice my cursor is still under the square root inside the parentheses. So if you just arrow over twice, you'll be outside those parentheses and ready to multiply by 42. And when I hit enter, I get 127.306. And again, this was a units and this was a units, so I am units squared. Whatever my units are, they're squared. So if you ever come across a 30, 60, 90, you don't have to do trig. If you come across a 45, 45, 90, you don't have to do trig. If you don't remember your special rights, then by all means, use SOHCAHTOA. Okay? Questions? All right, your assignment is available in Schoology.
Are our special rights going to be on the equation?
Yeah, you'll still get the same formula chart you got last time. Yes. Because this test will have just a couple, like 2 or 3, 45, 45, 90, 30, 60, 90. But again, you can always use trig. It'll have a couple Pythagorean theorem problems that you can't use trig. You have to use Pythagorean theorem. And then the rest will be trig.